In this lecture, we're going to talk about the basics of sensation and perception. We're going to define what those terms mean, talk a little bit about how they relate to one another. Basically, these are the two processes that allow you to take information from the environment and put it into your mind. It really underlies your ability to know what's going on around you. We're going to start off with sensation. So you can think about sensation as the input of raw information. Basically, it's your ability to detect physical energy that's within your environment. This can come in several different forms. You have light waves or sound waves that are detected by specialized receptors in your eye or your ear. In this image here, we have a depiction of different light waves, and this illustrates how the properties of the waves influence what you perceive. Things that appear red have a longer wavelength. Things that appear blue or purple have a much shorter wavelength. Physical energy can also come in the form of chemicals. So here we've got the molecules that represent different types of odors. So as these molecules float through the air, they enter your nasal cavity and they're detected by specialized receptor cells. As they attach to these receptors, they're processed, cause a chemical reaction. Eventually that information winds up getting sent to your brain. The really key component of sensation is a process that's known as transduction. And this is where that physical energy gets converted into a neural signal. So you're taking that energy and you're transforming it into something that the brain can process, the brain can understand. This occurs entirely within the sensory receptors. So basically, you can think about it as kind of a computer. You're providing some sort of input, the receptor is doing some kind of processing, and the output, the end result, is an electrical or chemical signal that eventually gets sent along this pathway that winds up in the brain. The image here shows what is happening in the visual receptors. A photon of light strikes a pigment that's known as rhodopsin, and this triggers this cascade of chemical reactions. Eventually, this causes a change to the physical structure of the receptor cell. It stops releasing a certain chemical, and that triggers activity within a neuron. That triggers activity within another neuron. Eventually, that winds up in the visual portion of the brain. What the receptors are doing, and what is the main process of sensation, is this transduction. It's this conversion. So what you're saying is that the brain does the perception part. Yes, but there are some caveats. What's happening in the brain is that it's getting all of this incoming information, and it really has to try and make sense of it. So perception is this really active process of constructing some kind of mental representation. You can think of it as interpreting what's coming in from the sensory receptors. So if we have three people here looking at this colored square, probably some people are going to look at it and think, no, this is pink. So that's the representation they form. Other people are going to look at it and think, hey, this is fuchsia. And then you're probably going to have somebody that's walking over from the other side of the building that looks at this and thinks, oh, this is Pantone 232C. But in all cases, you can see that they're looking at this object and they're forming some kind of mental interpretation. This is going to be influenced by several different factors. As you can see in this example here, one of those factors is the type of experience that we have. So if you have a lot of experience working with color, you'll probably form a different representation than someone with less experience. Another factor that influences the type of representation we form is the type of input that the brain is getting. So if we throw a fourth person in here, and let's say it's somebody that has cataracts, well, they're going to form a different representation because the input is going to be altered. In cataracts, the lens of the eye starts getting cloudy, and this blocks some of the light waves from entering. So in effect, you're really degrading the quality of the sensory input, and that's going to have a direct impact on the type of representation that's formed. Another influence, and a very important one on perception, is attention. Now, attention is a very limited resource. You only have a certain amount of attention that you can direct to everything that's happening around you, and direct to whatever sort of thinking that you're doing. You can kind of think of perception as a pie chart, in which a certain percentage gets devoted to maybe the work that you're doing. Another gets devoted to maybe listening to some kind of music. Third gets devoted to monitoring what's happening behind you. But in all cases, that attention is finite. You can't attend to unlimited things. Basically, you have to filter out a lot of the unimportant stuff. And so if you're concentrating on a work task, you may not be paying too much attention to what's happening in the conversation behind you, or to what somebody on the other side of the building is doing. Most of the time, you can choose where and how you want to direct your attention, but it can be captured. So if I ask you to think about how your foot feels inside your shoe, you're probably devoting more attention to it than you were like 10 seconds ago. Another example of this is if you're working and you're focused on something and somebody behind you says your name. You might not have been paying any attention to that conversation before, but now all of a sudden your attention gets captured. And you think, what? Hey, somebody talking about me? I hope they're saying something good. The fact that we can choose where and how to direct it means that we can devote a lot of attention to a task that we think is important. But this can have potentially negative consequences because we may miss other things in our environment. Case in point, one time I was driving to a friend's house to meet my wife, who was already there. This was in an unfamiliar part of town, so I didn't really know exactly where I was going, somehow navigated to the street, and this was also in the days before GPS. So I'm driving down the street, and I'm going about 5 miles an hour because it's getting dark, and I'm trying to look for this address. So I'm driving, and I'm squinting, and all of a sudden, bang! Crashed right into the back of my wife's car. Attention was so focused on figuring out this stupid address that I completely missed this giant SUV sitting in front of me. And even though I was only going 5 miles an hour, it was still hard enough to cause the airbags to release, and it ended up being a huge mess. Luckily, there was very limited damage to her car, a little bit to mine. Probably deserved it though. Bottom line is that if you don't attend to something, it's not going to be perceived. You're not going to form a mental representation of it. Here's another example of that. Which of these represents a real penny? Now, I'm going to give you a few seconds to think about this while I go track down an actual penny so that I know the correct answer. Turns out it's A. I've done this in class a lot. Every time I do this, two of the most popular answers are G and I, although a lot of people also say J. So why does this happen? Presumably we all have a lot of experience with pennies. When I did this in class, I often talked about my extensive experience as a college student with pennies because I really had no money and lived on a diet of ramen and cheap coffee. We all have seen pennies, we all interact with pennies. Why don't we know exactly how they look? We don't really need to attend to the fine details of a penny to know that it's a penny. All we really need to know is that it's a smallish coin, it's copper, it's got Lincoln on it. It's got to be a penny. Don't need to encode all of that other information, so we don't bother processing it. We don't want to waste our limited resources on something that we really don't need. It's our way of being efficient with our mental effort. So attention is a really big component in perception. And I posted a couple of links on MindTap about other experiments related to attention that kind of have somewhat surprising results. Another influence on perception is known as top-down processing. Perception is driven by these two really complementary processes. You have bottom-up processing, which we've talked about already. That's where incoming information is detected by your sensory receptors. That information gets sent up to the brain, and your brain puts it all together. Again, that's known as bottom-up. Top-down processing occurs when you have some kind of knowledge that influences your interpretation. You have some kind of experience or expectation. In this case, we can look at the checker shadow illusion. Squares A and B are the exact same shade of gray. Very difficult to believe, so what I've done is constructed a couple of slides where we're going to cover up a big portion of the checkerboard. And when you cover enough up, you can see that A and B really are the exact same gray. If you don't believe me, you can go back to the full figure and use paper to cover up your monitor, and you'll see the exact same thing. So what the heck is going on here? Well, again, you've got prior knowledge. You know what a checkerboard looks like. You know it's a series of alternating light and dark squares. And so you're imposing that framework onto what you're seeing, and you're interpreting this image in a way that's consistent with that knowledge. So even though A and B are the exact same shade, you're not seeing it that way because it's not what your experience tells you should happen. These top-down influences are a big part of visual illusions. In that previous example, there's this lack of correspondence between the interpretation that you form and the reality of the stimulus. In effect, these visual illusions are a way of tricking your brain or forcing it into a particular type of interpretation. And they can tell us a lot about how your sensation and perception systems operate. So you can look at these snakes here, and you should see that some of them appear to be moving. Now what's interesting is that the one that you are directly looking at should appear stationary, and that as you shift your eyes around the figure, the one that you're staring at, the one that's in the center of your vision, is stationary. The others appear to be moving. If you want to get these to stop entirely, just back away from your monitor until the whole figure is in your central vision, and then it should just remain stationary by itself. But as you start getting closer, then the stuff on the periphery should begin to move. So what's happening here? Why is this occurring? It happens because our central vision has much higher acuity than our peripheral vision. When you're looking at this figure, items in the periphery are slightly blurry, but there's such a high contrast here between the adjacent colors that the cells in your periphery are kind of switching on and off. They're going black, white, black, white, black, white, black, white. And that type of switching is consistent with movement. The appearance of movement is something that is imposed by your brain because it says, well, this is what typically happens when I have this kind of input. So we perceive the rotation there even though it's not actually present. Here's another type of visual illusion. Which face looks male and which looks female? Now, if you look at the faces very closely, you should notice something slightly strange about them, and that it's the exact same face. This face is actually a composite of several dozen faces. So this is kind of like the average face. Both male and female were combined, and this is kind of what the average looks like. The faces were created by reducing the contrast between the overall complexion and the shade of the eyes and lips. In the one on the left, that contrast has been increased. The face has been lightened, the lips and eyes have been darkened slightly. The face on the right, that contrast has been reduced. So the face has been slightly darkened and the lips and eyes have been slightly lightened. And what we have is something that looks female on the one hand, but male on the other hand. Again, this is driven by what our expectations and experience tell us. Third one here, which of these monsters is larger? And as you might guess, they're both the same size. But again, we have this prior experience, and we have all of these depth cues in the larger figure. So we see the tunnel, we see it going back or outward, and we see one monster that looks farther away than the other. And we know that as items get closer, they tend to get bigger. We think, okay, as this monster starts approaching, it's going to be much larger than the one that's in the foreground. And we kind of impose that onto our representation of the further monster. We don't see them as the same size. We see the one that's further away as being bigger. So we've got all of these different kinds of influences on perception. So when we say that perception is very individual, we mean that two people can look at the same objects, but because of the way that their senses function and because of the type of experience and knowledge they have, they may interpret that item totally different ways. To summarize, sensation, transduction, perception. Raw input, conversion to a neural signal, and interpretation. We've got a lot of different influences. We've got influences that can affect what's happening on a sensory level, but we have all this other knowledge that we bring to bear onto the type of representation we form.